Okay, so now for chapter 15, which is the final chapter in the textbook, and it's all about the chi-square statistic, which is the test for goodness of fit and independence. So the statistical tests that we've talked about so far have tested hypotheses about the population parameters, and those are called parametric tests. Parametric tests share several assumptions: that there's a normal distribution in the population, that there's homogeneity of variance in the population, that numerical scores exist for each individual, and they require data for an interval or ratio scale. If the research situation does not conform to the requirements of a parametric test, then a non-parametric test is needed. And this is an alternative test that does not state the hypothesis in terms of a specific population parameter, makes few assumptions about the population distribution, and involves two non-parametric tests called chi-squares. Non-parametric tests usually classify participants into categories. So you use nominal or ordinal scales, and those non-parametric tests have data that may be aligned in frequencies. Sometimes it's not possible to obtain the interval and ratio scale measurements, and it can be undetermined or infinite scores that are measured that we may not be able to characterize. So when it comes to choosing between a parametric and a non-parametric test, and most of the time, we're going to make that decision based on the level of measurement. So you could choose to test the significance of the relationship using a chi-square, a t-test, or a ANOVA, or you could choose to evaluate the strength of the relationship using R-squared. So the chi-square test for goodness of fit answers research questions about the proportions or relative frequencies for a distribution. It also uses sample data to test hypotheses about the shape or proportions of the population distribution. It can also test the fit of the proportions in the obtained sample with the hypothesized proportions of that population. So if we look in figure 15.1, we can see the distribution of exam grades for 40 individuals. And we can see those numbers. We can see the X and F values and it in the chart. The null hypothesis for the goodness of fit test specifies the proportion or percentage of the population in each category. It also provides a rationale for the null hypothesis with no preference among categories or no difference in a specified population from the proportion in another population. Because the null hypothesis for the goodness of fit test specifies an exact distribution for that population, the alternative hypothesis simply states that the population distribution has a different shape. So that could be as brief as not accepting the null hypothesis, which is often equivalent to the population proportions not being equal to the values specified in the null hypothesis. When we look at the data for the goodness of fit test, there is no need to calculate a sample mean. Individuals are classified in each category, and the observed frequency is tabulated for each measurement category. Each individual is counted in one or only one category. When we look at the expected frequencies, we have to look at the goodness of fit test, which compares the observed frequencies from the data with the expected frequencies predicted by the null hypothesis. We also have to determine the expected frequencies that are in perfect agreement with the null hypothesis. The expected frequency is the frequency value that is predicted from that null hypothesis with the sample size. It typically represents an ideal hypothetical sample distribution. So when we think of that, when we take all those things into account and we think about the chi-squared statistic, we have these symbols for notation, and here is the formula. An example of the chi-square test for goodness of fit is used in the sample 15-2 with that numerical value measured by the discrepancy between the observed frequencies and the expected frequencies. In this case, the proportions of observed frequencies in the sample are not expected to exactly equal the proportions in the population. So we've got a small chi-square value that meets a goodness of fit between the data and the null hypothesis. So that null hypothesis should not be rejected when that discrepancy between the observed and expected values is small, and it should be rejected when the discrepancy between the observed and expected values is very large. And so that chi-square distribution is going to include the values for all possible random samples when the null hypothesis is true. All chi-square values should be greater than 0. And when the null hypothesis is true, the sample x2 values should be small. The chi-square distribution is positively skewed with the distribution and degrees of freedom. And that chi-square is a family of distributions which are determined by the degrees of freedom. It can have a slightly different shape for each value of the degrees of freedom. And C is the number of categories that are there, and the degrees of freedom is not related to that sample size. So we're going to have degrees of freedom equals C minus 1. So if we take a look at figure 15.2, we have the chi-square distributions that are positively skewed, and we know that it's positively skewed because the tail tells the tail. So the frequent, most numbers are on the lower side. And in figure 15-3 or 15.3, the shape of the chi-square distribution is different depending on the value. When we locate the critical region for a chi-square test, we have to determine the significance level of alpha. We also have to locate the critical value of the chi-square in the table called the chi-square distribution, which is in Appendix A in your book. It'll show us the value for degrees of freedom in the first column, and also the significance level that's chosen for alpha. It can also tell us the critical values of the chi-square and the numbers listed in the table. So in figure 15.4, you can see the critical region, for example, 5.2. And when we get ready to report the results for a chi-square, that report should describe whether there were significant differences between categories, and the report may also provide the observed frequency for each category. The goodness of fit and single sample t-test is a non-parametric test versus a parametric test. The chi-square test for goodness of fit makes no assumptions about the parameters of the population distribution, and the t-test assumes a normal population, which requires numerical scores and test hypotheses about the population mean. Similarity can occur when both tests use the data from a single sample to test hypotheses about a single population. The level of measurement can determine the numerical scores to make it appropriate to compute a mean and use a t-test, and classification in non-numerical categories makes it appropriate to compute proportions or percentages and to use a chi-square test. So if we do our first learning check, it is the expected frequencies in a chi-square test are A, B, C, or D. Go ahead and take a moment to think about what the correct answer might be. And here you go, B, can contain frequencies or decimal values. Here's a true-false question. In a chi-square test, the observed frequencies are always whole numbers, and a large value for chi-square will tend to retain the null hypothesis. Take a few moments and think about the correct answer. And the correct answers are going to be true and false. The observed frequencies are just frequency counts, so there shouldn't be fractional values. And the second one shows that a large value of chi-square indicates the observed frequencies differ a lot from that null hypothesis. When we look at the chi-square test for independence, the chi-square statistic can also test for evidence of a relationship between two variables. Each individual can jointly classify each variable. Those can count as presented in the cells of a matrix, and those designs may be experimental or non-experimental. The frequency data from a sample are used to test the evidence of a relationship between the two variables in the population using a two-dimensional frequency distribution matrix. The null hypothesis is the two variables are independent, showing there's no relationship that exists between the two. And there are two versions. There's a single sample with each individual measured on two variables, showing there is no relationship. Or you could have two or more separate samples where there's no difference between the distribution of variables in the two populations. Those variables can be independent if there is no consistent predictable relationship. When we think about the observed and expected frequencies, those frequencies in the sample distribution are observed frequencies for the test. Those expected frequencies are based on the null hypothesis, which is a prediction of the same proportions in each category. The expected frequency of any cell is jointly determined by its column proportion and its row proportion. Those frequencies computed by the same method for any cell in the frequency distribution is indicated like so. And for the chi-square statistic for degrees of freedom, we use the same equation for chi-square test of independence as the test for goodness of fit. So let's summarize the chi-square test for independence. This is a test for independence that uses the same procedures as all the other tests. We're going to state the hypothesis, select that alpha level, locate the critical region, compute the test statistic, and make a decision. When it comes to effect size and assumptions for those chi-square tests, a significant chi-square hypothesis test shows the differences that did not occur by chance. Those tests of the significance are influenced not only by the size or strength of the treatment effects, but also by the size of the samples. And the outcome of that hypothesis test should be accompanied by a measure of the effect size. So we can look at Cohen's W, which can be used to measure the effect size by both types of chi-square tests, and the PO values, which are observed by proportions. The Cohen's W will also suggest that 0.10 is a small effect, 0.3 is a medium effect, and 0.5 is a large effect. Cohen's W does not use the sample size, therefore the sample size does not affect the value of W. The W is calculated using only the sample proportions and the proportions from the null hypothesis. W and chi-square are algebraically related to each other. So when we think about a 2x2 matrix, each variable has exactly two values, and the phi coefficient will measure the strength of that relationship, as indicated by this formula for Kramer's. When there's a larger matrix, we can modify the phi coefficient to be used with the effect size of Kramer's V. And in figure 15.8, we can see the standards for interpreting Kramer's V. And we can also make some assumptions and restrictions for chi-square tests. There are several conditions which must be satisfied to use a chi-square test for goodness of fit or a test for independence. Each observed frequency is generated by a different individual, and those chi-square tests should not be performed when the expected frequency of any cell is less than 5. So let's go ahead and do another learning check. And a basic assumption for a chi-square hypothesis test is what? Correct answer is C. The observations must be independent. Here's some true-false questions. The value for the degrees of freedom for a chi-square test does not depend on the sample size, and a positive value for the chi-square statistic indicates a positive correlation between the two variables. That's going to be true and false. The value for the degrees of freedom for a chi-square test depends only on the number of rows and columns in that observation matrix, and the chi-square cannot be a negative number, so it cannot accurately show the type of correlation between the two values. And here in example 15.3, we can see the SPSS output chi-square test for independence and the numbers that would be used. And here's more of those charts. And hopefully this information will help you guys understand a little bit more about the chi-square test.